Okay, today we're going to talk about arrays. So often it's convenient to have a large collection of variables that are all of the exact same data type. For example, let's say you want to write a program to store information about students in a class. All of the data we store about students is basically the same, but there are many of them, right? So imagine we had a class of maybe 300 students. You could see here we certainly could declare 300 individual student variables, maybe appending a number at the end of each variable name like this. So student 1, student 2, student 300. And then of course we could process all 300 students worth of information. For example, we could gather their names. Right? So for all 300 students, that's going to add up to quite a bit of work. Okay, so there's a large amount of code required to do anything with this collection of individual pieces of data. Okay, all of the processing though is essentially the same. So it would be nice if we could put this code in some kind of a loop. Right, so if we learned about loops just last week here. So we know we can do something 300 times, and we know the something that we want to do is really not that complex. Right? We just want to prompt for a name and then store that name. The problem is, how do we address each one of those 300 student variables? Okay, an array allows us to do something like this. Okay, but we identify all the values with a single name instead of 300 individual names. Each variable has a unique name. So an array is just a contiguous group of variables, all of the same data type, accessed using a single name and an offset from the first element in the collection. So contiguous, that word contiguous is just a fancy word for right next to each other. All of these variables are going to be right next to each other in memory. Okay, so here's what an array looks like. Okay, so imagine we had all 300 names here. Each one of these individual boxes holds a string, and you can see that there are some names in there. And the entire array has a single name. It's called students. And then we have these numbers underneath. These are used to identify individual names of our students. Okay, so syntax-wise, the way you create an array would be something like this. Let me go back to my picture here. Okay, so here's an example of creating an array of exactly 3 floats. Okay, so the rule with arrays is if you can declare a piece of data that has one item, you can declare an array of as many items as you'd like. In this case, I'm just asking, when the flow of control gets to this line, it says to the computer, go create room for 3 floats. Make sure they're all right next to each other in memory. And we're going to give a single name to this group of 3 floats. We're going to call it grades. Okay, now each one of the 3 floats inside here has this thing called an offset or an index. Okay, and the offset or index always starts at 0. So the name refers to the first element of the array. And then you place a number inside square brackets to select an offset from the beginning. So for example, now when the flow control gets to this point, it says grades at position 0, we want to assign the value 71 to that individual float. Okay, what this means is go find the thing called grades, right? That's this group of data. Go to position 0, and then store the value 71 inside that box. And then when the flow of control gets here, this says go find the thing called grades, go to index 1, and store the value 84 there. And then lastly, when the flow of control gets here, grades at position 2 is equal to 99.5. That says go find the thing called grades, move over the size of 2 floats, okay, and then that's going to give you access to this chunk of memory right here. We're going to store the value 99.5 there. Okay, so arrays don't save us any space. 300 strings in an array take up the exact same amount of space as declaring 300 individual string variables. The benefit is that there's a single name to address all of them. So now we can go back to this code here. And now this is how I would write the code to declare 300 strings for each one of my 300 students. And then I'd write a simple little loop, just a 2 or 3 line bit of code here to march all the way through each and every one of those strings, okay, using the square bracket notation. And then we would read in values, and they would be stored inside each one of those individual names. Then when I wanted to print them out, okay, I would do something like this. Again, I set up this little for loop, and I just go and access each one of the individual string values. So this value I, that's the counter. The counter is going to vary from, in this case, from 0 to 299. So let's stop and think about this for a second. The loop counter starts at 0. Okay, so why is that? Well, this is because the first element is addressed by moving 0 elements away from the beginning of the array. Okay, so in anytime you access an array, when you say grades at 0, this says go find the thing called grades and move 0 elements away from that address. Right, so this is grades, and then grades plus 0 is the exact same spot. This refers to a box, and that's why 71 goes inside the first box. Grades at 1 says go find grades and move the size of 1 float over. Right, that gives us that address, which is the beginning part of a box, and that's why 84 goes at position 1. And grades at 2 says go move over 2 floats. That's the starting point of the third box, and 99.5 goes in there. Okay, so our loops are always going to start at 0, and they're always going to be less than the size. So the loop in this case would go from 0 to 299. So the loop test in this case, while I is less than 300, means that the largest number that this will result in being true is 299, not 300. Because 300 is not less than 300. 299 is the largest value that's less than 300. Okay, so if you start at 0 and you go to 1 smaller than the size of the array, your loop counter will actually be the index of each and every one of the different elements inside the array. A very common error is to be off by 1 in a loop that processes elements of an array. So make sure your loop counter always starts at 0 and goes to 1 minus the size of the array. You can put any integer or any whole number inside the square brackets. So you could do something like this. We looked at a couple loops where we had a loop counter in there. If you wanted to do some arithmetic, you could do that, as long as the result ends up being an integer. Okay, so here I'm kind of moving around plus and minus 10, or plus 10 and minus 1 places away from this value I. You have to be very careful, though, not to go outside the bounds of an array. Okay, let's look at our float array again. So here we have grades, right? And there are definitely some boundaries here. This array has a start and an end, and the boundaries are listed like this. Now if you were to do something like this, let's say I said grades at position 3 is equal to 98. Okay. Well, we kind of have a problem here, right? Because really there are only 3 elements in the array, and now I've gone to, this is actually the 4th element, okay, or what would happen in this case is, with C++ arrays, when you give the name of an array and a set of square brackets, the computer will calculate the offset no matter where it is and give you access to that memory location. Okay, this happens even if the index in the square brackets is not within the bounds of the specified array. Right, so when I say grades at position 3 is equal to 98, that says go find a thing called grades, and then move over the size of 3 floats. Here's 1, 2, 3. That gives you access to this box right here, and we're going to store the value 98 right there. Okay, and this is actually a really bad thing. It may not seem like a big deal, right? So what if we use a little bit more memory than we said we were going to use, right? Memory is cheap, so what's the what's the problem? What's the big deal? Well, let's take a look at this code. Okay, so here we have this declaration of this float called num. Okay, and we set it equal to 100. Okay, so let me draw what our memory would look like. Okay, so initially we have kind of this wide open chunk of memory, and now I'm declaring a float called num, and I'm going to set it equal to 100. Okay, and let's just say that in this run of the program, that variable num just happened to land right here. Okay, but next we have this declaration of an array of 3 floats called grades. Okay, well, again, let's just say that in this particular run of the program, grades happen to land right here. Okay, so in a program, we never really know where the variables are going to land in memory. Okay, that's why we have names. We don't really care about addresses. We just deal with names. Okay, so we have, grades just happens to be right here, which is right next to the variable called num. Okay, so what happens next? Well, we have this loop, and notice we have a problem here. The loop is going to go one element too far. So I is definitely going to start at 0, and while I is less than or equal to 3, we're going to say grades at position I is equal to 0. Okay, so I is going to go from 0 to 1 to 2 and to 3, because 3 is equal to 3. So what's going to end up happening is we put 0 there, 0 there, 0 there, and this is the really bad part. When I is equal to 3, okay, grades at I says 1, 2, go over 3 positions, and then we have access to this box, and we're going to put a 0 there. 0.0. That's what our loop says we're going to do because of that equal sign here. Okay, now imagine some code very far away from this, probably written by a totally different person. Okay, and they're going to look at this variable called num, which remember we declared up here. And we're going to say, well, if num is greater than or equal to 50, we're going to do something. Okay. But look at the value of num. It used to be 100. But it's not 100 anymore, it's 0. Okay. So num is definitely supposed to be 100, and therefore this if should definitely evaluate to true, right? Because nowhere in here have we changed num. We assigned it here and we're checking it here. It definitely should still be equal to 100. Okay, but it's not. And in fact, this if will evaluate to false. Okay. Why? Because 0 is not greater than or equal to 50. So anyone looking at this code would definitely expect the if to evaluate to true. Okay, so that's why this is a bug. The code kind of makes it clear that one thing should happen, but if you look at the data in memory, that says something different. This is a very hard bug to find because it's not the person who made the mistakes code that won't work, the person who went outside the bounds of the array. It's the innocent bystander whose code's not going to work. It's the guy who is working with num, right? His code's not going to work. And the innocent bystander will assume that he made the mistake, right? It's his code that he's working on. And he's going to spend a lot of time trying to figure out exactly why num is not equal to 100. And he'll be scratching his head, and it's just going to take him a very long time to figure out, what is going on. So here the perpetrator wrote over someone else's data and there were no error message, no warning signs. That's how it works in C++. The program happily walked over some data because the programmer writing that loop didn't stay within the bounds of his code. Okay, what makes this even more maddening for the innocent bystander is that when the program is run again, the variables might land in some other location, and the error won't pop up anymore. So now you know there's this problem. You've seen it happen once, but you can't consistently recreate it. And Albert Einstein had this saying. He said, "Insanity is doing the same thing over and over again and expecting different results." Well, after dealing with bugs like this for many years, you actually start to do this. You actually start to expect different things to happen when you run the exact same code. So I don't know what that says about us programmers, but it's a little disheartening when a bug like that slips in your code. Okay, so you have to be very careful with arrays and using this square bracket notation. Let's talk about some things you can do with arrays. Some little shortcuts. One thing you can do is you can initialize an array. You can initialize an array with multiple values in the declaration, and that looks something like this. So this says, when the flow control gets to this point, this says, go create room for 3 integers, and we're going to call that group of integers model years. And notice the syntax here. We have a set of curly braces and this comma-separated list of values. These are going to populate the first 3 elements of the array. So model years at 0 will be 2012, model years at 1 will be 2013, and model years at position 2 will be 2014. Okay, and this is really just a shorthand notation. You could have done the exact same thing like this. You could have declared the array, and then in 3 steps right below it, you could have initialized the 3 pieces of data. So this just saves you a few keystrokes. It saves the programmer from having to type a few things. Okay. You can even leave this is the only time you can leave a number out of the square brackets when you declare an array. So you can leave the size of the array out when you initialize it, and the compiler will go and count the number of values inside the curly braces and basically fill that number in for you. So we can thank our compiler for allowing us to not having to put a number in here. The compiler can just count these and put the 3 in there for us. Okay, now let's talk about some things you cannot do with arrays. There's a lot more things you can't do with arrays than we can. Okay, so for one thing we can't do with an array is we can't do just really simple input and output. So this code that I have here is actually, this is not valid. This would not compile. Okay, so it looks like you kind of want to ask the user to put in 3 values and then maybe print those values out. Well, you can't do it like this. You can't do it in one step like this. You can do it, you just have to do it in 2 separate steps, okay? And you have to have a loop that's going to allow you to do that. So the first thing we're doing, reading in the values into the model years array, we need to set up a loop that goes from 0 to 2. Right? In an array with 3 elements, the index values are 0, 1, and 2. And what this is going to do is repeatedly prompt for a model year, and then we're going to see into model years at position I. And again, model years, or I is going to be 0, 1, and 2, and we're going to have access to each one of the 3 elements in that array. If we want to print out all the values in the array, again, we're going to need this loop where we march through and grab each individual integer by itself and do a cout. Okay, so you can't do input and output. Another thing you can't do is you can't assign one array to another. So here we have another integer array called tax years. It's exactly the same size. It has 3 elements. The data type is exactly the same. They're all integers. So you'd think you'd be able to do something like this. Kind of say, for each one of the 3 values in model years, store them in the 3 tax years. Okay, but unfortunately we cannot do that. Okay, we can't do it easily anyway. We can't do it in one line. What we have to do is we have to write a loop to do that. So this will create the array of 3 integers, and then we have to, again, march through here. So 0, 1, and 2. we're going to basically copy from model years to the corresponding position in tax years. Okay, we cannot do arithmetic of whole arrays. So again, here we have two arrays who they're the exact same type and the exact same size. So you might think it'd be nice to be able to just positionally add these three values together: 4 plus 1, 5 plus 2, 6 plus 3. Okay, unfortunately you cannot do it like this. You have to write a loop to do this. Okay, and again we go in and using our loop counter, we access each one of the arrays at the same position, the corresponding position. We do the arithmetic and then store the result. I just happen to store them back inside array 1. Okay, so array 1 should now have 5, 7, and 9 after this loop executes. Okay, we cannot compare whole arrays together. So again, it'd be kind of nice if we could say, well, is this array, are all the elements in this array exactly the same as the elements in this array? Well, we can't do that, not with the double equals. We can, however, write some code to do this. And you'll see this is quite a bit more complex. So this creates our two arrays and fills them. Then I have this Boolean that's supposed to hold true if all the elements are the same, and false if even one of the elements is different in either one of the two arrays. So what we're going to do is we're going to go through all of them, and well, actually, what I decided to do was assume that the two arrays are identical. So arrays equal to true, and only if I find out otherwise, by marching through and comparing the array at position I with array 1 at position I with array 2 at position I. If those two are not the same, then I could say, well, my arrays are definitely not equal. I can put a false value in here. And then as soon as I find one of the values that's not the same, there's no point in looking at the rest of them, so I can break out of this loop. And now arrays equals that Boolean, that holds the true or false value that says whether these arrays have exactly the same values inside them. And in this case, of course, arrays equal would be equal to false. Okay, so as you can see, almost all of the work done with arrays happens inside for loops. That's why in the last lecture I really emphasized the importance of a for loop. Since almost all programs have to process many similar pieces of data, so think of payroll processing at Walmart, for example, where they have basically 1 million hourly workers, right? The calculation to figure out an hourly worker's pay is not that complicated, but they have so many workers that it definitely makes sense that you'd want to do that inside a loop. Okay. So this is a very common operation, being able to iterate through a loop, through an array like this. And this is going to be a very important part of your programmer's tool belt. Okay, let's talk about a few other things we can do with arrays. We can have two-dimensional arrays. So a two-dimensional array is a collection of data in a table, okay, where there are rows and columns. Okay, so notice here we have an extra set of square brackets when we declare the array. So this says, when the flow of control gets here, this says, go create this thing called table. There should be exactly 3 rows and 4 columns worth of integer values. Okay. So let's look at a picture here. So here we have that same declaration. So again, when the flow of control gets here, this says, go carve out room for 3 rows and 4 columns worth of integers, and give the whole thing the name. I'm just calling this one table. So notice here, each row has an index number that starts at 0, and each column also has an index number. Starts at 0 and goes to, again, 1 minus the number of columns. Okay, so when you do this, we always put the row number first and the column number second. Okay. Now we can actually fill values inside this table using the same square bracket notation we used before. So table at 0, 0 equal to 1, that means go to the table, go to row 0, column 0. So row 0, column 0, and put a 1 there. Next we have table at 0, 1, so always row first. This is always be the row. Column 1, so 0, 1, that's here. We're going to put a 2 there. If we say table at 1, 2, that means go to row 1, which is actually the second row. Column 2, which is actually the third column. And we're going to put a value of 7 there. And then table 2, 3. Okay, row 2, column 3. We're going to go there and put a 12. Okay, so the first square bracket always selects the row number. The second one always selects the column number. Oftentimes you'll want to process all of the elements in an array. For example, let's say we wanted to sum up all the values in the table. We could do something like this. Okay, so here we have this variable called sum. We're going to start it at 0. And then basically we have a nested for loop. We talked about that in the last couple of lectures also. So we have this counter called row. That's going to span through all the valid row numbers. So 0 through 2 are the row numbers. And then on the inner loop we have this other loop counter called column. And that's going to go through all the valid column numbers from 0 to 3. And then we're going to use the row and column number inside this little expression here to extract out each one of the values and add it to a running sum. So the sum starts at 0, and then we're just going to start summing these things together and storing the result back in the sum. And of course this loop should iterate this line here should iterate 12 times. 4 in the inner loop times 3 in the outer loop for a total of 12 times. Okay, sometimes you want to process just the elements in a particular row. So let's say we wanted to print the elements in just the second row. Okay, well, the second row has a row number of 1. Right? So this is the second row here. Okay, so what's going to vary now is just the column number. So column's going to go from 0 to 3, and we want to hard code the row number. Again, the first set of square brackets is always the row number. Okay, and what should happen here is we're going to sum up the values in just the second row. And a similar loop can be made to go through just the columns of a table. So it turns out you can have a 3-dimensional array, or a 4-dimensional array, or a 40-dimensional array. This, of course, is a 2-dimensional array. It's kind of like a 2-dimensional picture. Well, like I said, you could have a 3-dimensional array. Right, so let's say we wanted to keep track of 10 items that we're selling over the last 5 years. So there's 12 months in each year. Here's 5 years. Okay, we can keep track of these 10 items of sales. We can maybe keep track of how many of these things we've sold by creating a 3-dimensional array. So each one of the rows represents an item. Each one of the columns represents a month. And then and the third dimension here, each one of these represents each one of the 5 years. Notice all the index values start at 0, and we go to 1 minus the actual size. Okay. So it's pretty hard for me to wrap my head around more than a 3-dimensional array, since I can't easily draw that picture. But the computer has no problem with it at all, and we'll take a look at how the computer deals with multi-dimensional arrays in a second. So a multi-dimensional array just lays out rows next to each other in memory. So let's look at it right now. So let's look at this declaration here. This says, when the flow of control gets here, this says, go create room for a 3-row, 2-column array called ARR. So here are the 3 rows and the 2 columns. And if I wanted to go and store something at array 2, column 1, this just says go find a thing called array, go to row 2, column 1, and store the value 10 there. Well, really how the array is laid out in memory. Memory, I've always been drawing it as this kind of one-dimensional long series of boxes. Okay, and that's definitely how you should think about your memory. So how do we deal with this two-dimensionality or n-dimensionality? Well, basically the compiler knows when you declare the array how many rows and columns there are going to be. So when I do something like this, and the compiler knows that each row will have 2 elements in it. Okay, so the 2 in the declaration specifies how many columns there are going to be in each and every row. So the compiler does a little bit of math to figure out how to access the element. Okay, so it basically takes each row and it lays it out in memory right next to each other. So we have, these are the 3 individual rows, and then when we say something like this, go to row 2, column 1, it really takes the row index, right, this is the 2, and it multiplies by the number of columns there are, 2 times 2 is 4, and then it takes the column index and adds that to that value. So 2 times 2 is 4, plus 1 is 5. So it says go to the array and go to position 5. So it'd be 0, 1, 2, 3, 4, 5. And that's where we'd store the value 10. Okay, so it's all kind of a trick that the compiler does for us. Figures out, it lays out each row on its next to each other, and then when we use the square bracket notation, it does a little bit of math from what it knows about the size of the two-dimensional array to give us access to any one of the elements. Okay, so arrays are very, very useful. We're going to be using them pretty much all of the time. And again, that's because a lot of the time we're going to process large chunks of data. That's one of the great benefits of writing a computer program, is that we can process not just tiny pieces of data, one or 2 pieces of data, but huge amounts of data. As long as it's in an array, we can go through that array and process all of that data.